Hello everyone, a very good morning to all the students present in today's lecture of digital communication. Is my voice properly audible?
Yes.
Okay, thank you for the response. So, till last lecture we have started looking at digital carrier modulation scheme, namely ASK, FSK. Today we will kickstart PSK, the phase shift keying, and specifically the Bpsk, the binary phase shift keying, and Qpsk, quadrature or quaternary phase shift keying. But before we begin, let me ask very simple few simple questions from you people, and I'll call your names. So, Shreya Thakkar, can you listen? Jay Chopra, can you listen?
Hello.
Jay, can you
Yes, sir.
differentiate between a non-continuous FSK and a continuous FSK, CP-FSK, and a non-continuous phase FSK?
Frequency shift keying.
Yes. So there are two types in that. One is
Yeah.
non-continuous phase, another is continuous phase. So can you differentiate between these two?
No, sir. I did not remember yesterday's lecture.
Okay, no issues. No. Drupad, can you listen?
Hello.
Drupad, can you listen?
Yes, sir.
Drupad, can you answer this question? Difference between a continuous phase FSK and an FSK with the non-continuous phase.
Sir, I haven't attended the last lecture because I was out of the town. That's why.
Okay. Then let me ask from Nandini. Kashyap. Kush Patel, can you listen? Atriya Patel. Ankita Dimri. Am I audible?
Yes, sir.
Aman Narayan, can you listen? Acha, who will answer this question? Is continuous and non-continuous phase, which is related to your frequency shift keying. Who would like to give a try? We have seen in the very last lecture. Anybody?
Sir, starting and ending point of the two phases are not same in non-continuous. Means they are different. Means their places are different.
Yes. So there is phase discontinuity which is happening in a general Fsk, right? And it is not good. So what do? We obtained a continuous phase frequency shift keying in which the transition from one phase to another phase is smooth rather than an abrupt change in phase. And how do we ensure that? Can you answer? How do we achieve it? CPFSK? So we plan our mark and space signal frequencies such that they are integral multiple of bit rate divided by 2. In that manner, your ending of a bit duration always will end up at the 0%. So it will be in the multiples, maybe 1, 2, 3, like that. So the phase, the ending of the bit duration will not lead to any discontinuity in the phase. Are we good, all students? Or shall I create a poll that you are learning at good pace? Okay, maybe I'll create a poll at the end and let us have more interaction during this lecture. So we proceed with our topic of Psk. That is the phase shift keying. Okay, so I'm sharing my screen. Is the screen visible?
No,
Sir,
now it's visible.
Okay, thank you. So we start our topic of phase shift keying, Psk. So again, like different modulation, digital modulation schemes, one the amplitude of carrier we vary, we call it as Ask. When we vary the frequency, it is Fsk, and when we vary the Psk phase, we call it as Psk. So both Fsk and Psk, they are which part? They are angle modulation schemes. Okay, so Fsk, since it is part of the angle of the sinusoidal term, similarly phase is also a part of that angle. So these angle modulation we have just this is a common term for both Fsk as well as Psk. Fsk and Psk. So Psk is again angle modulated and a constant amplitude modulation scheme. The amplitude does not vary. Whereas in Ask you are having amplitude which is variable. Okay, constant amplitude angle modulation scheme. So in Psk, what do we do? In Psk, the input binary data, input binary information is encoded into groups of bits. Okay, before modulating the carrier. Now, how many groups, how many bits per group? That is a question, and that essentially forms the different forms of your phase shift keying. So the number of phases, since phase is changed, so the number of phases which you are having after the modulation, the number of output phases is defined by, say, capital M, and this capital M is determined by the number of bits which you are grouping, the number of bits in a group. Let us represent this with small. So we will have 2, 4, etc. number of bits per group, and then based on number of groups we will have number of output phases. Okay, so this is a general PSK, but our main topic is Ppsk and Qpsk. So we first take the Bpsk, that is the binary phase shift keying. In Bpsk you have n as 1 and m as 2, 2 to the power n, so which is 2. So that means you have 2 possible output phases. Hence, it means we have 2 possible phases, and we have 1 bit each group. Rather than we can call it as 1 bit, there is no group. So there are 2 possible phases. So since it has 2 possible phases, it is also known as AKA, also known as PRK. PRK stands for phase reversal keying. Okay, or also known as biphase modulation, since there are 2 phases. And since these phases are just the reverse of each other, it is also known as phase reversal keying. So we'll look into more detail, but this remember, Bpsk is also known as PRK and BM, biphase modulation. Okay, so how do we generate a, are we good, students? So far?
Yes, sir.
Okay. So if you look at a Dpsk transmitter, so you have your binary data as input. I'm writing input means input, okay, and this is fed. Then you need a circuit known as level converter. What is level converter? Somebody has ever heard of? So essentially your binary data is presumably in unipolar format. If it is in bipolar format, then you don't need a level converter. But if it is in a unipolar format, you require a level converter. This level converter, what it will do? So unipolar, if you write as UP, then this level converter will convert unipolar to bipolar. What is the difference between unipolar and bipolar? Anyone? Yes, please. This is a very simple question. Polarity. It is related to polarity. What happened, students?
Sir,
Let
for
us.
bipolar, we take -1 for 0 bit.
Very good. Yes. Like that, I want all people to participate proactively. Very good. Who has answered? Can you spell your name?
Aditya.
Aditya. Very good. So this is your unipolar to bipolar conversion, and you will see why do we need a level converter. Why do we need a bipolarity bipolar signal. Okay, so you are feeding this bipolar input to a balanced modulator. Now this balanced modulator is taking this input bipolar data as one input, and another input is the sine omega ct. It is the reference carrier signal. Okay, and after that, if you are simply filtering it, you need filter to remove unwanted components. Then you are led with the modulated Psk output. O oblique P means output. So this is short form I'm writing, but don't get confused. It is. This is a very simple modulator. So many times, you question what is this balanced modulator and what is this doing. Just I thought of bringing you to just exposure to ring modulator. Have you ever gone through ring modulator? Or you ever heard of ring modulator, ring circuit? If not, no issues, because we are going to discuss it. Aditya,
Yes, sir.
never heard of a balanced ring modulator
No.
in FSPC? Okay, no problem. We'll see. So remember, in BPSK we have two phases which are totally reverse of each other. First thing, so we take our binary data. If it is unipolar, we convert it to bipolar. Then we feed this signal to a balanced modulator. The another input to this balanced modulator is our reference carrier signal sine omega ct. The output of it is actually the product. Okay, we use a band pass filter to remove the unwanted components, and then we will look at the polarity of the output signal after the filtering. So we see with the help of one circuit we call as balanced ring modulator. This ring modulator is the same as that balanced modulator. So you'll come to know what balanced modulator is doing. Okay, so use of balanced ring modulator. The circuit might look like a little complicated, but it is very easy to uh, understand. Okay, so don't worry about it. This is the primary coil of a transformer. This is the coupling lines. This is the secondary side. I mean, just don't focus on these number of turns. This just take as equal. Then you have extension of this secondary coil side and usage of diodes. Okay, 1 minute. Again, you have coupling and this is output you are taking. So this diode is D1 and this is D2. You have another pair of diodes connected in this fashion. Like this. So here the input is your reference carrier signal input, which is nothing but your sine omega ct. At this, let us call this transformer as T1. This is T2 transformer. Okay, this is D1 diode, D2 diode, this is D3 diode, and this is D4 diode. This is D4. Okay, might look small, but this is D4 diode. This is T2 transformer. or let me write it here so that you don't get confused. This is D4 diode. Now this is center tap transformer, so we feed at the center of this winding what our binary data, bipolar binary data at this site, and at this center tap we are connecting it to ground, and here we get our modulated Bpsk. Now we'll see the working of this circuit, how it is able to produce two signals with phase exactly reverse with each other as per the binary data polarity. This is reference sine omega ct. What are these two lines? Can somebody say? This coupling. What does this denote? Have you ever seen these two lines in a transformer? Students, you have to speak rather than I call your names. So this is non-air coupling. Okay, if you do not draw these two lines, means air coupling is there. Okay, and these two dots, can you see across T1 and T2, these two dots here and here? You can see. Let us see who else are there. Let me take attendance also. Abhi Patel, can you listen? Adit Patel.
Yes, sir.
Adit, can you do you have any idea what are these two dots? These T1, T2, these two dots. Can you see? If you don't know,
Yes,
no
sir.
problem.
No, sir, I don't know.
Okay, no problem. So these two dots, which are shown here, T1 and T2, what does it mean? The windings are such a way that if the polarity here occurring is plus minus, similar polarity will occur at the secondary side. So if let me change color, if it is plus minus here, similarly because of mutual induction, the same polarity will be generated. If plus minus is occurring polarity at this, similar polarity will occur at the secondary side. So same polarity. But if these two dots are at different locations, like for example, let me remove it. This for just for your explanation. Otherwise, always remember these two dots are at same side, right? So same polarity it is generating. If it is like this, then if polarity here is plus minus, it will be reverse what will be induced in the secondary side. So it will be plus minus if dots are shown like this. I hope it is clear to everyone. Very small concept, but we should always remember this. Anyhow, coming back to our topic. So this is of the same polarity. So plus minus here will be induced. Similar way here also T2 also is the similar nature. Okay. Now these center tap we are provided with binary data. Binary data, again you remember, it is bipolar. Bipolar means it can be plus V, it can be minus V based on our bits. If it is logic 1, it will be plus V. If it is logic 0, it will be minus V. So just keep in mind this thing. Okay. Also, always remember, you have a carrier signal here and you have a binary bipolar data here. So the condition for this circuit to work properly is that for proper operation, the digital input data which you connected to the secondary side, its voltage or its level must be very high in comparison to your carrier signal peak voltage level. Okay, so always remember, it has got higher strength, higher voltage level in comparison to your carrier peak amplitude. Why? Because since diodes are used in this balanced ring modulator, and based on the application of the potential voltage level, these diodes may be on or may be off based on the polarity which is fed, based on the biasing, forward or reverse biasing. So the control of on and off operation of these diodes D1 to D4, it should be in the control of binary data rather than your carrier signal. So based on our binary data, we want our diodes to on or off. That's why the condition is for proper operation, digital input voltage must be greater than peak carrier voltage, so that the diodes D1 to D4 on and off operation is controlled by binary input data. If the input data changes 1 to 0, 0 to 1, so our biasing of D1 to D4 should change. Okay, so this very important condition always remember. Okay, so let us erase this thing. So how does this work? So let our binary data, which is input binary data, is plus V for logic 1 and minus V for logic 0, since it is a bipolar signal. So when take logic 1 is there, okay, so these application of plus V here, which diodes it will forward bias and which diodes it will reverse bias, please you have to say. Anyone? If I am applying a logic 1 here, which diodes will be forward bias? Please give a try.
D1 and D2.
Yes, D1 and D2 will be forward bias and they will be kind of switch on. This will be closed. So when you have logic 1, I'm just quickly recreating this circuit like this. This is coupling. So when D1 and D2 are on, At the same time, your D3 and D4 are off because they are reverse bias. This N side is connected to the positive polarity, so it will be reverse bias. So these D3 and D4, they will be kind of switch off. They are in off condition. They are reverse bias. So considering D1, D2 on, D3, D4 off, how the circuit will look like in that case? Just quickly I am drawing. It's this T2 side, this T1 transformer, T2 transformer, and this also will be connected. So this our plus V, this our ground, and these two dots are there. Here input is sin omega ct. Since these two dots are on the same side, same polarity signal will occur. The same polarity signal is reaching to this primary coil of this transformer T2. Since these dots are also same side, so similar phase signal will be generated at the output of this T2 transformer. So reference carrier sin omega ct, you apply a positive voltage, the circuit becomes like this. Same sin omega ct is able to reach to the output of this transformer T2. So this is when it is happening, when D1 and D2 they are on, and D3 and D4 they are off. Is this clear to everyone? Okay, and these are not connected. Let me just clarify with you. This is like kind of jumper. Like this. This is put in ground. Okay. Is this clear to everyone? How application of logic 1 resulted into same phase signal, same carrier signal at the output. Yes or no?
Yes, sir.
Consider the another case when you have logic 0 applied at this point. So I'm quickly drawing using a red color. So this is T1. So this will become the reverse of this. So D1 and D2 will be reverse bias, hence off, and D3 and D4 will be forward bias, hence on. So how the circuit will look like in that case? This point will be connected to this side of your coil, and this point will be connected because D3 and D4 they are connecting. Okay, and again this is, they are not crossing each other. Okay, like this. This is not crossing, this is jumper kind of thing. This is T1, this is T2. This is the output of T2, and what is applied under this condition? Minus V. So if sin omega ct was applied at this input side, sin omega ct same will be appearing at the secondary output, but this positive terminal, this positive polarity, it is now getting connected to the opposite side of this coil. If through this diode, like this diode become, this D4 diode become on. So this point is connected here and this point is connected here. So what polarity will appear here at the input side or the primary side of this T2 transformer will be opposite of what is appearing at the secondary side of this T1 transformer. If plus minus is appearing here, this plus goes here and this minus goes here. So ulta polarity you will get here, and similar is induced here. So when sin omega ct is here, what we are getting at the output is minus sin omega ct in this case. And under such condition, your D1 and D2 they are off, and D3 and D4 they are on. So you can see with the application of bit logic 1 and bit logic 0, you have either same phase or opposite phase as output of this T2 respectively. Is this clear to everyone?
Sir,
Hanji.
how the two different signals can affect the diode, the reference carrier and the binary data, because these are two different signals.
Two different signals are there. So essentially, we are trying to modulate the phase of this carrier signal. है ना? By the definition of modulation, what do we say? Modulation is the process in which we vary some characteristics of the carrier signal. Now our carrier is sin omega ct, and in phase shift keying we are modulating what? Phase. So this is the first case of phase shift keying, which is binary phase shift keying. And how many phases we have? M equal to 2. So how we have selected those phases? Totally reverse phases. One will be 180 degree out of phase with, or one will be the negative of the carrier. So if you are feeding sin omega ct, reverse of this is minus sin omega ct, isn't it?
Yes, sir.
Because sin pi plus theta is minus sin theta.
Yes, sir.
So pi means 180 degree, है ना? So that is means both the input and output, they are 180 degree phase apart. So our intention was to modulate the phase, and we are successful in generating different phases of the carrier sin omega ct on the basis of application of either we are applying logic 1 or logic 0. If logic 0 we are applying, we are getting a 180 degree phase shifted version of the carrier. If we are applying a logic 1, we are not getting any phase shift. We are getting the same phase, or we can say a 0 degree phase shift.
But sir, my question is that at diode we have two signals. So how the diode is taking this reference?
Okay. Good question. What is your name?
Nirbhay Parmar.
Okay, Neil. Sorry, if I'm not wrong, Dheer, है ना?
Nirbhay, sir. Nirbhay Parmar.
Nearby. Good. So if you remember the first condition, which we assumed that the binary data voltage level is very high in comparison to the carrier signal peak amplitude. If you remember this,
Yes,
before
sir.
we started, है ना? That is just to ensure that the switching on and off of diodes is totally in control of binary data, not
Yes.
at all carrier amplitude. So if this you are taking 1 volt na, or some volts, definitely you have to take it 3 volts, 4 volts, 5 volts, like that. The voltage level of binary data has to be. So binary data voltage is playing major role, or the only role, sole role in controlling the biasing of the diodes. The carrier is used only for phase wala matter, है ना? The on and off is totally controlled by binary data. So that's why there will not be any impact of your carrier amplitude on the biasing of D1, D2, D3, D4. They are solely controlled by binary data input. Am I clear now? Okay.
Yes, sir.
Okay. Good question, Neil. And I hope it satisfies your query. So in this manner, we get two phases at the output, and this is what? This is our ring modulator. This is the inside of the balance modulator. You always see this block diagram now, balance modulator, balance modulator. What is there inside? This is the ring modulator, example of the balance modulator circuit. So always remember, balance modulator means this arrangement. Okay, so with this, let us take. So if you represent these logic 0 and logic 1 in terms of phases, how would you represent? So we call that as truth table. So the truth table is simply the table containing details about the binary data logic and the phase shift which is getting introduced. So it is binary input and this is the output phase. This is the truth table. Only two combinations will be there because only two phases are there. So for logic 0, you will have 180-degree shifted version of the carrier. For logic 1, you have 0-degree phase shifted version of the carrier. This is truth table. The another way to represent this, there are two ways. One is the phasor diagram and another is your constellation diagram. Both are essentially the same. It's a matter of representation. So if I write phasor diagram, so as the name suggests, we'll represent something with phase information. Represents phase information. So we draw phases like this. So if you consider this as the reference sine omega ct, and this is also representing the logic 1 or 0-degree phase shift. This is 90 degrees apart, so this is plus 90 degree and cos omega ct. This sine omega ct, this will be cos omega ct, 90 degree apart. This will be what? Just opposite minus sine omega ct. Or we can say 180-degree phase shifted version. So in our case Bpsk, this is representing what? Logic 0, and this will be minus cos omega ct, or with reference to this is reference, okay, with reference to this is minus 90 with reference to this 0 degree. So we have two arrows here, two phasors. One is sine omega ct, another is minus sine omega ct. This is phasor diagram. Is it clear, everyone? And another is your constellation diagram. So constellation diagram, the same thing, to get confused. Just with that, we represent the phasors not with arrows but with dots. Okay, so the representation is different. So if you draw your axis like this is 0 degree or reference or logic 1. So here you have this dot, you can see this is one point in this constellation. This is phase space. In phase space you have two phases. In this entire constellation space you have one point which is representing logic 1. This is cos omega ct. This is minus cos omega ct. This is plus minus 180 degree with reference to this 0 degree, and this is logic 0. So in our Bpsk, how many points should be there in constellation diagram? 2 points. So the second point we'll draw here. So these are constellation points in the constellation space like this. Essentially both are same. Arrow we are using here to represent phases, and here dots we are using for constellation points. So this is constellation diagram. Is it clear, everyone?
Yes, sir.
Okay. this constellation diagram you will find very informative, because अभी इसके बाद we will see QPSK, then we will see MRE-PSK, and then we will see quadrature amplitude modulation QAM. So if you have understood the constellation diagram, the understanding of QPSK, QAM, MRE-PSK will be like very smooth for you people, right? So don't keep any doubt with this constellation diagram. This constellation diagram is also known as, just for your information, it is also known as signal state space diagram. Signal state space diagram. So now just have a quick go through with example binary data. So if I draw the reference axis for time duration, pardon if they are little bit here and there. Okay, I think sufficient. This is your, say, binary input. Let me draw. One zero like this. So this is your binary input. So if I ask you in PSK, what is the polarity of the logics, bit logics, you will always say bipolar. If I am using unipolar, it will not work. It has to be bipolar. So 1 0 1 0 1 0 and so on. So this is again this with the time this data is occurring. So the equivalent modulated output will be, how it will be looking like. So for bit 1 we have sine omega ct. Okay, let me draw one reference axis. So this is what? Sine omega ct, because bit 1 is there. Now bit 0 has come. What should happen? 180-degree phase shift. So this will be just reverse of sine omega ct. So this will be minus sine omega. Coming now 1. So sine omega ct. Again 0. So minus sine omega ct. 1. So sine omega ct. 0 minus sine omega ct. Minus sine omega ct, sine omega ct, and so on. So this signal is our Dpsk signal. Clear, everyone? If 1 had been here, same sine omega ct you will have to draw like this. If you have any query, any doubt, please share, or else we are good to finish this lecture today. I think sufficient we have covered. So now you should feel confident with the understanding of phase shift keying, specifically binary phase shift keying, and we define that we get reverse phases for bit logic 0 and 1. How do we do that? We make use of a circuit we call as balanced ring modulator. We also seen the inside of that balanced ring modulator circuit, how it is capable of producing reversed phases with reference to the applied bit input data polarity, and we are getting output phases. We have also seen them, represented them in time domain, in phase domain, and in constellation space domain. So if you have any query, please feel free to ask, or else we are good to finish this lecture. No queries? Just tell me frankly if it is okay, if you have understood. Everyone, any one of you can just quickly respond.
Hello, sir.
Hanji.
Sir, when you, when we will you share the code of SSB?
Today I will send. Yes.
Okay, sir. Thank you,
But
sir.
just answer my question. Have you understood today's thing?
Yes, sir. Yes, sir.
Why I am asking? Because the next coming things, they are built upon this core thing, this Bpsk. From Bpsk we will go to Qpsk, where we will have quadrature phase shifting. We will have 4 phases. We have M array Psk, means those many number of phase shift phasors we will have. Then we have an alternate version, which is a combination of Psk and amplitude modulation, is QAM, quadrature amplitude modulation. So that's why I'm emphasizing a lot whether you have understood or not this. Okay. So I believe it is clear to everyone. Thank you, everyone.
Thank you, sir.